Okay, so this particular video is going to be over just the concept of refraction. And if you remember from just taking a look at this as a vocabulary term, refraction does have to do with the bending of a wave. And this is the bending of a wave as it goes from one medium to another medium. So it's a change in medium or a change in substance that it's traveling through. So if we have, a boundary here and we have air up here and water down here, then if light, and I'll do this in a different color, if light comes in like this and it gets that medium or into that boundary, and we say it happens right there, the collision, the interaction with the boundary, then there is a bend in the way the light comes in. And if we talk about things in terms of this blue dashed line, the normal, right, this is the normal line, then this is an angle with respect to the normal that we call the angle of incidence. And the incidence just means that the angle, well, incidence means when it happens upon the entrance point. Entrance point is a good way of saying it. And then this angle down here would be the angle of refraction. It's the different angle between the entrance, and this would be the exit side. So why does this happen? I mean, we have seen this before, spoons and straws and glasses and things like that. Why does this happen? If you recall, we did that little exercise out in the hallway where this is happening because it's a change in speed, right? You have a higher speed, excuse me, you have a lower speed here, and you go into water. Uh, oh, well, we were talking about sound then. So actually, let me backtrack. If this is light, since we're talking about light now, light actually, since it does not require the actual medium to transmit through, then when you get into a denser material for light, not for sound, but for light, when you get into a denser material, what you're doing is you're putting more crap in its way, basically. You're putting more crud in the way of the light traveling. So as you go up in density, the air actually slows down. So this would be considered a fast medium, and this would be considered a slow medium. A light is slowed down, so it gets bent towards the normal. Remember, if it speeds up, then it gets bent away from the normal. And you can actually visualize this diagram as going either direction, going down into water or coming out from water. And it actually works either way. It gets bent towards the normal coming in and away from the normal going out. Well, how do we quantify this whole fast and slow thing? We do it by this thing called an index of refraction. Index of refraction. Index of refraction has a letter associated with it. It's called n, and n is simply the ratio between the speed of light when it's normal, in a vacuum, speed c, 3 times 10 to the 8 meters per second, to the speed that it's traveling when it's in this particular medium. So n is calculated as being the ratio or the fraction of c divided by v, where c is the speed of light and v is the speed inside a particular medium. Okay, the speed inside the particular medium. So just to kind of give a little example here, if we have something like, oh, I don't know, um, water. And water has an index of refraction of 1.33. Okay, and it doesn't, I'm just saying basic water. Salt water would actually be different. Has an index of refraction of 1.33. That means that 1.33 is equal to the ratio of 3 times 10 to the 8 meters per second over the velocity of the light as it's in the water. So how do we actually calculate this value? Well, we can flip and we'll just flip out the v for the 1.33. So v would be the 3 times 10 to the 8 meters per second divided by 1.33. And that is much slower than, I was going to bring up a calculator. It's much slower than what it is if it's in just a regular vacuum. In this case, the velocity would be 2.25 or 26 times 10 to the 8 meters per second. Okay, it's about a third as slow is what we're kind of dealing with here. Okay, so refraction has to do with a change in speed, between one medium and another. Well, that diagram that we have, and I'm going to redraw it, where light comes in at one angle and comes out at a different angle with respect to this normal line here. Okay, and remember that we have the angle of incidence and the angle of refraction. If this is in fact air and this is in fact water, then there's two different indexes of refractions. Here, n is equal to 1.0003. Don't ask me why I know that. It's just I've had to use it. And then down here, n is equal to 1.33. Okay, notice how n does not have a unit. It's unitless. It's one of our naked numbers that we have. And since it's a ratio between speeds, n should not have a number on it. It's just a ratio, right? How many times more does it slow down or things like that. But there's an equation that deals with all of this information, and this is known as Snell's law. Excuse me. Named after the guy who discovered it. It is Snell, and this is N1 sine theta I for incidence, or you can do Ni for index of refraction on the incidence side, is equal to N2 sine theta R. So given a little example here, if we come in at a 45-degree angle and we have our indexes of refraction, the question is, at what angle is it refracted? So we have the 1.0003 times the sine of 45 degrees is equal to 1.33 times the sine of the angle of refraction. So how do we go about solving this? Well, we can divide 1.33 to the other side, and we're left with the sine of theta r is equal to 1.0003 divided by 1.33 times the sine of 45 degrees. And to get the actual theta r, we would have to take the inverse sine of both sides. So we end up with an inverse sine of this, all this right here, 1.0003 divided by 1.33 times the sine of 45 degrees. And if you stick that all into your calculator, making sure that you're in degree mode, and making sure that you do the inverse sine at the right time, you get that the angle of refraction for this particular case is 32.1 degrees. So it comes in at 45 and it comes out at 32. Okay, the light has been bent for the sheer fact that it is being slowed down, and we've taken that into account by dealing with the indexes of refractions for these particular media. Okay. So we'll do more examples of this in class, and if you have any questions, you can let me know.